So we are live.
So welcome back. Welcome to the GATE Academy again. So this is our fourth session in the series of GATE 2021 added new syllabus. So in this series right now we are discussing the steam turbine and gas turbine that has been added in the GATE 2021 examination, that has been added in GATE 2021 examination. Okay. So on behalf of the GATE Academy, I would like to welcome you again. I would like to welcome you again. I would like to welcome you again. And in this video, what we are going to cover. So before that, let me first introduce myself. My name is Uma Shankar Tripathi, and as you can see in the slide, that our topic is steam turbine and gas turbine. So I am Uma Shankar Tripathi. Currently, I am a PhD scholar. Currently, I am a PhD scholar at IIT Roorkee. Okay, PhD scholar means people sometimes call us as research scholar. So in simpler words, I am pursuing my PhD. I am doing my PhD. Hello Rahul, hello Jamin. So currently I am doing my PhD from IIT Roorkee. So before joining into the PhD program, I have completed my MTech from IIT Roorkee itself, and for that I have qualified the GATE examination in GATE 2014. I had, Amesh, hello, 65.66 marks, and in GATE 15, 77.02 marks. So on the basis of my GATE rank in 2014, I had all India rank 916 in GATE 2014. On the basis of this rank, I got admission in, good afternoon. I got admission in IIT Roorkee in MTech program. So from last 8+ years, I have been teaching in this GATE domain for the GATE Academy. So this is our fourth lecture. So in this fourth lecture, we are going to begin the impulse turbine again. We have discussed something about impulse turbine before as well. So in this lecture, we are going to start with the impulse turbine thing. We are going to start with the impulse turbine again and going to analyze it. But before that, some of the nozzle part was left. To be discussed, and which is also a part of impulse turbine only. So first of all, we will conclude the nozzle in all respect. Then we'll move to the impulse turbine thing. Then we'll move to the particularly impulse turbine thing. So as I told you in the previous lectures as well, and if you have not seen the previous lectures or previous sessions, if you have not seen the previous lectures or previous session, just subscribe the GATE Academy English channel and watch them. Okay, this is the fourth lecture in this series. We are having this much lectures in this series. So this is the fourth number lecture. So if you want to understand it in a nicer way, just go and check out the previous videos as well, if you haven't seen them yet. Okay. So in the previous session, we have developed. I am starting with the where I have left in the previous session. So in the previous session, we have developed this expression for what? For convergent nozzle. Okay, for convergent nozzle. So as we have discussed earlier as well, for convergent nozzle it is. So as we have discussed earlier as well, impulse turbine is a combination of nozzle and steam turbine. So what we are talking here, so let's say our steam turbine is having a convergent nozzle. Steam turbine is having a convergent nozzle. What it is having? It is having a convergent nozzle. Like this. It is having a convergent nozzle, and we have established in our previous lectures that steam turbine is nothing but a combination of nozzle and moving blade. So here we go. In this steam turbine, we have this nozzle, and after the steam leaves that nozzle, it will go to the moving blade. So in this lecture, we will also analyze the moving blade. In this lecture, we will start analyzing the moving blade also. But before that, we should complete the analysis of this nozzle. So this is what, this is a converging nozzle. So why I am focusing so much about convergent nozzle? Because in 95% time in a steam turbine, convergent nozzles are used. Convergent nozzles are used. Now you will say, sir, why so? Now you will say, why so? Because as I told in the first lecture itself, that entry state of steam in nozzle or in steam turbine is at very high temperature. So if you focus the formula of Mach number, which decides the flow is sonic, subsonic, or supersonic. So if temperature is high, we can say our velocity of sound, which is gamma RT under root gamma RT, is also high. So the velocity, so the temperature is high. When the temperature is high, gamma RT, we can write it like gamma RT or gamma TR, doesn't matter. So gamma RT, so if temperature is high, C will be high and Mach number will be low. So the chances of having the velocities, the chances of the video, the chances of having the condition go in supersonic state is quite less. So mostly in practically and mostly the convergent nozzles are utilized. Convergence nozzles are utilized in steam turbine. Okay, that's why we are focusing so much on convergent nozzle. Is that clear? Is that clear or not? Okay. So what we have established, what formula you are seeing on the screen, is that let the entry to this nozzle is at state 1 and exit to the nozzle is at state 2. So this is the expression through which by putting the pressure ratio, we can find the velocity at exit of the nozzle. Velocity at exit of the nozzle. So N is P2 by P1. P2 by P1. Okay, P2 by P1. So I may call it the pressure at exit of the nozzle is PE. May I call the pressure at exit of the nozzle is PE, and entry to the nozzle is P1, or sometimes you can say P0. These all are the same thing, different nomenclatures used in different books. So do not get confused in it. Okay. So in the last lecture of the flow through nozzle, what we have seen. In the last lecture of flow through nozzle part 2, it is named by flow through nozzle part 2. What we have seen? We have seen this velocity can't be more than sonic velocity, can't be more than C in convergent nozzle. This is what we have seen. In where, if I talk about only convergent nozzle, this can't happen. Okay, this can't happen in a convergent nozzle. This is not possible. V2 cannot be greater than C. Cannot be greater than C. Jasmeet Joshi, whatever you are asking, I don't have idea about it. So V2 is greater than C. You must ask this. You subscribe this channel. You subscribe the GATE Academy English channel. You will get the videos here in the recorded form. After this live lecture, videos will be here. Don't worry about it. Okay. So V2 is greater than C is not possible in the convergent nozzle. Till this point, we have seen in the previous lecture. Now, listen to me. Velocity is related with pressure. We all know velocity is related with pressure. So if V2, what can be the maximum velocity? If I say, tell me what is the maximum velocity you can achieve while using a convergent nozzle. So maximum velocity at exit, you can respond in the live chats. Maximum velocity at exit is equal to V2 is equal to velocity of sound. Maximum velocity at exit can be the velocity of sound. It can't be more than that. We cannot, in a convergence section, we cannot achieve the velocity more than the velocity of sound. This is what we have seen in the last video, in the last session. Yes or no? And at the point where we attain the velocity of sound is called the critical point or choke point. Critical point or choke point. Critical point or choke point. Okay. So now tell me this. If we cannot increase the velocity, now listen the verse very carefully. If we cannot increase the velocity above c, if we cannot, if our Vmax, if our Mmax is equal to c, so we know when we increase the velocity, the pressure is decreased. So corresponding to this velocity, there must be a pressure, and that pressure we may call the minimum pressure. This velocity of sound we achieve at the throat, which is represented by 2 here, So maximum velocity at the exit is the velocity of sound. We cannot have the more velocity than it. In the same way, velocity is very much related with the pressure. We cannot reduce. Listen to me very carefully. We cannot reduce the pressure. From a certain value. So the minimum pressure we attain in a convergent divergent nozzle is what we call as critical pressure. And at this critical pressure, if we find the pressure ratio, we will call it as critical pressure ratio. So if I summarize the thing, in a convergent nozzle, we increase the velocity, but we can't increase it above the velocity of sound. Okay. Similarly, the next statement is in convergent nozzle, we decrease the pressure, but this pressure couldn't be decreased. This pressure can't be decreased more less than a certain value. It can't be below a certain value. So as we have established in the previous lectures as well, that in nozzle velocity increases and pressure decreases. So the increase of velocity can't go beyond a point, can't go beyond a value, and that value we know is the velocity of sound. Now what we have to now know is what is that critical pressure value? Below which our exit pressure can't go in a convergent nozzle, below which our exit pressure cannot go in a convergent nozzle. So what I can do for that, I can put the value of maximum velocity. So I am going to do at critical condition, at choke point, or you can say critical condition. At critical condition means what? We are talking about the throat. And at critical condition, our exit velocity is going to be equal to the maximum velocity, and which in turn is equal to the velocity of sound. So in this above equation, I'm just going to put V2 is equal to C. So if I write V2 is equal to C, my equation will become somewhat like this. 2 times Cp, and in the previous lecture I have shown you how we can play with this temperature, pressure and density. We can write this equation in terms of pressure and density as well. For that, you have to go to the last session you have to see. Okay, this is the extension to the last session. Okay, so please subscribe the GATE Academy channel and go and watch that also. Okay, so we have this N, and let's call it PC by P1 to the power gamma minus 1. Why I'm using this PC? Because I am calling it as critical pressure. So I just have put the value of pressure ratio as PC by P1 by assuming that now my pressure is being reduced to the critical condition, that is Now my pressure is reduced to PC, and as I told you, now the pressure can't be below this PC. Our exit pressure, as we have said here, our velocity at the exit can't be more than C. So pressure of exit can't be less than the critical pressure, because at critical pressure we achieve the velocity of sound. So here we go. I have put the value of C here. I have put the value of C2 here. Why C2? Because we are talking about the exit. It is V2 now. So we have to talk about the velocity of sound at the exit. So we have V2 here. So I can place C2 is equal to, I can write like this, C2 is equal to gamma R T2. C2 is equal to nothing but gamma R T2, and this will become just simple mathematics I am going to follow. So 2CP T1, 2CP T1, 1 minus PC by P1, 1 minus PC by P1 to the power gamma minus 1 by gamma. Can we write like this? So certainly we can write like this, no problem at all. So we can just square both sides. We can just do the squaring of both sides, and we can write. So let's call it CC, because we are using the subscript C for the exit pressure. So just call it CC, no problem. You can call it 2 as well, but for that you have to know that we are now calling 2 points as critical points. So if in order to do not create any confusion, in order to not having any confusion, we call it CC, no problem, because we are talking at critical condition. This is just subscript. You can use anything you want. So I am just using gamma RTC. So I can write it like 2CP T1 1 minus PC by P1, 1 minus PC by P1 to the power gamma minus 1 by gamma. 1 gamma minus 1 by gamma. So here we go, gamma RTC 2CP T1. 1 minus PC by P1. So what is our target? We have to find in this there are two critical properties. In this there are two critical properties. One is temperature, critical temperature, and one is critical pressure. Okay, so what should be my approach from here? I should convert this equation into either in terms of critical temperature or either in terms of critical pressure. So I may from here can choose to go either way. Either I can change it to critical pressure terms. I can change it to critical temperature terms. Doesn't matter. So what I am going to do, let's see. So I am going to convert temperature into pressure, and going to find what. So going to find the value of critical pressure. So from CP I can write gamma R gamma minus 1. We have seen in the last lecture, and we know it already by our basic understanding of thermodynamics. Yes or no? Those who are in live, they can respond to me if they feel any difficulty. This is nothing but the play of the equations. This heavy equation we have just developed by using continuity equation and Euler equation and steady flow energy equation that you already know. So you have to see all the lectures to understand. If somebody is seeing just from here, he won't be able to understand. So you have to watch all the lectures, all the sessions, then only you will be able to understand the concept of it. So here we can cut this gamma, we can just cut this gamma, and TC by T1, since we have assumed that our flow is isentropic, we can certainly use this relation. TC by T1 is equal to PC by P1 to the power gamma minus 1 by gamma to the power gamma minus 1 by gamma. Yes or no? We know this is from, as we have assumed all the things into isentropic, all the things as isentropic, so we can write like this, and I am just cross multiplying. So we can write like this: PC upon P1 to the power PC upon P1 to the power gamma minus 1 by gamma, Pc upon P1 to the power gamma minus 1 upon gamma. So from here we can write gamma minus 1 by 2, gamma minus 1 by 2, or we can write just take Pc by P1 to the power gamma minus 1 by gamma as common. Pc by P1, Pc by P1 to the power, Pc by P1 to the power gamma, gamma minus 1 by gamma, gamma minus 1 plus 1, gamma minus 1 upon 2 plus 1. So, Chain, you are asking a very good question, sir. When we know where to apply which equation. So for that, I have recommended this in the previous session as well. Now I will recommend this in this session as well. That this velocity equation you need not to remember. You can develop this equation in very few steps. 2 or 3 steps will be required if you have some basic understanding of Bernoulli equation, steady flow energy equation, and a continuity equation. You need to require, see, for understanding the flow through nozzle for compressible flow, you only require 3 equations. From that 3 equation and some basic understanding, you can develop any equation you want. Okay, so right now, see, right now I am developing the equation. There can be in number of equations in this chapter. You can develop in terms of pressure, critical pressure someone can ask, critical temperature someone can ask, critical density someone can ask. So it is not possible to memorize all these equations. So what we can do, we choose what if I would be in your place, what would I have done? I would have not memorized a single formula out of it. I would just be solving by the basic understanding what I have of some fluid mechanics concept and some thermodynamics concept. Is that clear, Shayan? So I recommend you do not remember any formula. Just approach from the very basic as I have told you. Yes or no? Yes or no? So from here we can write as Pc by P1 to the power gamma minus 1 upon gamma. So if we do it, it will be equal to gamma plus 1 by 2. So if I send it there, I will send it there. So it will be like 2 upon gamma plus 1 upon gamma minus 1 by gamma. So this relation is very, very important. So I have showed how you have developed. This relation. We can send this here. So gamma upon gamma minus 1 we can write. So I told you how we have developed this equation. So you can choose to memorize this equation as well. But if I would be in your place, I wouldn't have done it. I will go with the basic understanding. But this critical pressure, why I am deriving in terms of critical pressure, because this question, because compressible flow was already there in ISRO syllabus, in Indian Space Research Organization syllabus. So the questions of critical pressure are being asked in that examination too. So it is very tentative that this critical pressure is going to be asked in GATE examination as well. Okay, so from here we can develop Pc is equal to P1 2 upon gamma plus 1 upon gamma upon gamma minus 1. So now if we have the value of gamma, we can have the critical pressure provided we have the inlet pressure. To the turbine. So here we have developed a very important formula of critical pressure, and at this critical pressure, if I find the pressure ratio, I will call it as critical pressure ratio, and it is generally denoted like this, N star. So N star is nothing but critical pressure ratio. So this is our critical pressure and critical pressure ratio. Got my point? Now see. For example, we'll do an example here. But before that, let me tell you something. Let me make you understand the things even more better way. So let us have some equation. We are having some equation. We are having some equations. So if we have the value of gamma, if we have the value of gamma, if we have the value of gamma, we can certainly find this PC. So let's say we have found this PC and this PC is equal to 5 bar. This PC is equal to 5 bar. So definitely the entry pressure will be greater than this pressure. Let's say our entry pressure is 20 bar. I'm just giving you an example. Okay, so let's say the entry pressure in a convergent nozzle, entry pressure in a convergent nozzle is 20 bar. Entry pressure in a convergent nozzle is 21. This is condition 1 and this is condition 2. This is condition 2. Now listen to me very carefully. Listen to me very carefully. Is it necessary that every time this exit pressure reaches the value of critical pressure? So no, it is not always necessary. It is not always necessary. So my first question, can P2 be equal to 15 bar? Now you can answer. Can P2 be equal to 15 bar? Can P2 be equal to 15 bar? Tell me yes or no. Tell me yes or no. So yes, it can be 15 bar because 15 bar is above the critical pressure. 15 bar is above the critical pressure. So we can expand our steam to any pressure above the critical pressure. No problem in that. So let me ask you again. Can exit pressure of nozzle, can it be 10 bar? Can it be 10 bar? Now tell me yes or no. Can the exit pressure of the nozzle be 10 bar? Is it possible? Yes or no? Now tell me yes or no. Think about it. Think about it. Yes. It can be 10 bar. Very good. Yes. It can be 10 bar. Why? Because this pressure is greater than critical pressure, or sometimes we may call it choking pressure. So this pressure is greater than the critical pressure. So yes, we can achieve this pressure in our convergent nozzle. No problem in that. Now one more question. Can our PC is 5 bar? Remember that. So can P2 equal to 5.1 bar? 5.1 bar. Now tell me yes or no. Can P2 is 5.1 bar? So you would say yes sir, it can be equal to 5.1 bar because we are still above the critical pressure. So P2 when greater than PC, So if any question the exit pressure is greater than PC, which pressure you will use? So you will use, if in any question you will find the exit pressure to the nozzle. Sometimes it is called as back pressure as well. Although back pressure and exit pressure may be different also, but for time being we are considering that back pressure, exit pressure of the nozzle are same. In this condition are the same. So now listen to me very carefully. If in a question is something is like that, that the inlet condition to the nozzle is this, back pressure is this. So what you have to do? You have to first calculate the critical pressure. Then check if the back pressure is above. If the back pressure is above the critical pressure, then there is no problem at all. As we have mentioned, there is no problem. And and we don't have to use the PC value. We can use P2. We can use P2 or PB, we can say. Back pressure, we can say. What is PB? PB is back pressure. So if PB is greater than PC, if PB is greater than PC, we have no problem. If PB is greater than PC, we have no problem. If PB is greater than PC, we have no problem. And we can use, if PB is greater than PC, we have no problem. And we can use exit pressure as equal to the back pressure, as equal to the back pressure. Now tell me, can 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 P2 equal to 5 bar? That is exactly is equal to PC. Exactly is equal to PC. Now tell me yes or no. Can this happen? Can this happen or not? Can this thing happen or not? Tell me that. Tell me that. This thing happen or not? So yes, this can also happen. This can also happen because we have seen in the last session, that when the critical condition has reached, so at PC we have seen in the last lecture that the velocity, will be equal to the velocity of sound, and we will have the minimum possible area. We will have the minimum possible area at this point. We will have the minimum area at this point. And we will call it as throat. This is something which respond to throat. So now things you have to relate with each other. Now when the exit pressure is equal to critical pressure, now I am writing it here. When exit pressure is critical pressure, when exit pressure is equal to critical pressure, the exit velocity is equal to the velocity of sound. The exit velocity is equal to the velocity of sound. And in the last session we have seen that we can achieve this point in a convergent nozzle. We can achieve this point in a convergent nozzle, and at that point, when this thing has achieved, the area of at that point will be minimum, and that what we call as throat. Got my point, Frozen and Chain? You said no, we can't have this. So we can have this if we make the minimum area. That we call throat. So at critical condition, at critical pressure, we have the critical velocity or the exit velocity equal to velocity of sound. Got it or not? Chair. Got it or not? So this is also possible. So if let's say the back pressure, what we have seen earlier, that if the exit pressure is equal to back pressure, and this back pressure is greater than the critical pressure, we have no problem, and we can use P2 is equal to PB. We don't have to use the value of PC. Now at critical point, the P2 will become equal to PB, the back pressure, and this pressure P2, PB both are equal to PC. So we have no doubt we can use P2 is equal to PC, or you can say PB. All are same. Now tell me, can again a question. Can P2 go less than 5 bar? 5 bar we are taking as our critical pressure. So can this happen? Means our P2 has gone below critical pressure. So this can't happen. So what is the answer? This can't happen. This is a big no. This can't happen in a convergent nozzle. This can't happen in a convergent nozzle. So if now listen to me, if P2 if P2 if P2 is equal to PB is given to be less than PC, can you use P2 is equal to PB? Can you use P2 is equal to PB? No, you cannot use P2 is equal to PB. You cannot use P2 is equal to PB. You cannot use P2 is equal to PB because we cannot attain this much pressure in the nozzle. We cannot attain a pressure below the critical pressure in the nozzle. So here in this question, you have to use, here in this question, in this kind of cases, you have to use P2 is equal to PC. So when to use the exit pressure equal to back pressure, when to use the exit pressure equal to critical pressure. Is that clear or not? Is that clear or not? It will be more clear after our question. So let us have one question here. Let us have one question here. Is that clear or not? Is the discussion clear or not? So it will be more clear after you solve this question, after you see this question. So let me just increase the font of it. So now you can see a question on your screen. Now you can see a question on your screen. So let me raise the font a little bit more. Okay. Now it is very much visible. It is very much visible to you. Now, could you please start solving the question? Though I am waiting, I am taking a pause here. I am taking a pause here for 2 minutes, 3 minutes, and I want everyone to attempt into this question. I want everyone to attempt this question. And before you see this question, let me show you the formula. Let me show you the formula of our critical pressure. So this is the formula of our critical pressure. You can have it noted down, or you can take a screenshot of it. Of this, I'm talking to the students who are live in this class. Okay. Just solve this question. You will have the idea. Just solve that question. You will have that idea. Just take a note of this critical pressure formula. Just take a note of this highlighted critical pressure formula. Just take a note of it. Just take a note of this highlighted critical pressure formula. And then we'll go to the question. So I hope all of you have taken the photograph or written this formula. Then we can go here. In examination, you can choose to memorize this formula, or either you can derive it as I told you to solve for it. If the concepts are clear, within 2 minutes you can derive. Within 2 minutes you can derive. Because certainly these formulas are very hard to remember. These are big formulas. Now please solve this question. This concept will be clear to you, that when we have to take the critical pressure for solving the question, when we have to take the exit pressure, the back pressure. So again, while you solve the question, please subscribe the GATE Academy English channel, as well as we have a Hindi channel as well. Subscribe that also. Okay, subscribe that also. So in this, the GATE Academy, we are providing you with this new syllabus. We are covering the new syllabus in all respect. In the steam turbine and gas turbine series, we almost have covered the compressible flow as well. Okay, so it is very beneficial to all of you. Please share it with your friends also. Share the video, like it, like the page of the GATE Academy on Facebook as well, on any social media platform, so that we feel motivated and will produce these kind of videos even more frequent. Okay, absolutely free live video session series, live session series is going on. Okay, where we are completing in all respects the new syllabus being added to the GATE 2020 examination. Okay. So to motivate us, to motivate the GATE Academy to doing the right things for the well-being of the students community. Please support us. Now, anyone can give me the answer to this question? Any students who is live students, can you answer me? How to approach? Some spelling mistakes are there. This is isentropic. Is entropically means isentropic. This is enters. So you have to calculate mass flow rate here. You have to calculate mass flow rate here. Okay. Now, someone can give you a big formula of mass flow rate as well. Mass flow rate as well. But I think from the basic understandings, from the basic what you know about mass flow rate, you can solve. You can solve. Everyone know mass flow rate is rho AV. So if you follow some books, you will have a big formula of mass flow rate ready for you. So you may choose to memorize that as well. Okay. But I won't recommend it. Just try to solve it from the very basic concept we have seen. Just try to correlate, just try to solve it from the very basic concepts we have seen. So in this, there are two cases. In this, there are two cases. Yes or no? Someone was asking me, who was asking me, Amesh, you were asking me, sir, which formula to be used where? Which formula is to be used where? How we will come to know? So here I am going to use just one formula of critical pressure, no other formula we are going to use. Just from the basic concept we are going to do. But first of all, I want every one of you to solve this question. Those who are seeing this video, this recorded video, are also expected to solve this question so that you can follow the lecture throughout. So if you solve this question right now, you will feel like you are live only. Okay, that is why I'm taking a pause here. Any answer? Any answer? Any answer? Any answer? Any answer? Anyone want to give? Any answer anyone want to give? Any answer anyone want to give me? Okay, so I am going to solve this for you. I am going to solve this for you. Now listen to me. Now focus on the screen. I will solve it for you. So what is given to us? Now listen. If you haven't solved it yet, the live student, please listen to me. First part I will solve. Second part you may solve. So we are having now here, here having a convergent type of nozzle as given in the question. So what are the entry conditions? What are the entry conditions we are having? What are the entry conditions we are having? So we are having, let's say our entry condition is 1 and our exit condition is 2. Exit condition is 2. So what is the entry condition we are having? So if you read the question, please take a screenshot of it, the live students. So this P1 is 7 bar. We have given as P1 is 7 bar. P1 is 7 bar and T1 is 97 degrees Celsius. So let's convert it. Let's convert it into Kelvin. So it will be 370 Kelvin. It will be 370 Kelvin. Is that fine? Okay. Okay. And the back pressure is 3.5 bar. The back pressure is 3.5 bar. Okay, so we have a back pressure, we have a back pressure, we have an inlet pressure, we have an inlet pressure. So how we must approach? First thing, how we must approach in this question? How we must approach in this question? So firstly, we should check. Firstly, we should check that our convergent nozzle can achieve this back pressure or not. See the procedure how we are going to solve this question. This procedure you can apply in many similar kind of question, and with this question all your concepts will be crystal clear. Okay, so firstly we have to check that whether our convergent nozzle can reduce the pressure of 7 bar to 3.5 bar. For that, how we can check? How we can check? So for that, we have to find our critical pressure. We have to find our critical pressure. So what formula we have seen? What formula we have seen? We have seen the critical pressure formula as equal to PC is equal to P1 2 upon gamma plus 1. 2 upon gamma plus 1, 2 upon gamma plus 1, gamma upon gamma minus 1. This is the formula what we have seen. This is the formula what we have seen, right? This is the formula what we have seen, isn't it? This is the formula what we have seen, where it is. Okay, this is the formula what we have seen now. This is the formula what we have seen now. PC upon P1. PC upon P1. So this is the formula 2 upon gamma plus 1. 2 upon gamma plus 1 upon to the power gamma upon gamma minus 1. Gamma upon gamma minus 1. So you have P1, you have P1, you have P1. So this pressure depends upon the inlet pressure and the value of gamma. Or in other words, we can say that this critical pressure ratio depends upon the value of gamma only. The value of gamma only. So in this question, the value of gamma is not given to you. Values gamma is not given to you. So firstly, let us calculate the value of gamma for case 1. So Cp is given to you as 5.19. 5.19, and molecular weight, this is not the Mach number, mind you, this is molecular weight. Molecular weight is given to be 4. So molecular weight is given. So from the basic concept of thermodynamics, we can calculate our R. R is nothing but universal gas constant upon the molecular weight. We know that, yes or no? So from here, we know the universal gas constant is 8.314 and molecular mass is given to us as 4. So this R is going to be 2.0785. 2.0785. Yes or no? This can go. This R is 2.0785. So we know that R is equal to Cp minus Cv. These equation we know from the basic classical thermodynamics, which was already there in the syllabus, and we also know that Cp by Cv. We also know this, that gamma is equal to Cp by Cv. These two things we already have knowledge about. Okay, so if we have R, we have Cp, we can find the Cv. So just put the value of Cp and R here. So we will have the value of Cv as 3.115 kilojoule per kg. And if we put the value of Cp and Cv, the value of gamma will be found, and it will come out to be 1.667. So you can check, the live student can check the calculation with me as well. So we have this value of gamma. So we can have the value of critical pressure ratio. We can have the value of this critical pressure ratio PC by P1, we can have this value of PC by P1, PC by P1. So let us put the value of gamma in this equation. Let us put the value of gamma in this equation number 1. So can you tell me what is coming out to be? So 2 upon gamma plus 1, that is 1.667, 1.667 plus 1, 2 upon gamma plus 1 to the power gamma upon gamma minus 1, that is 1.667 upon 1.667 minus 1. 1.667 minus 1. So can you tell me what is the critical pressure value? What is the critical pressure value? We have the value of P1 is equal to 7 bar. P1 is equal to 7 bar. So P1 is equal to 7 bar. P1 is equal to 7 bar. So I am using the red pen here. P1 is equal to 7 bar. So PC. So PC will come out to be PC. So I am writing this with red so that you won't make any mistake. This is very critical. So this PC is coming out to be 3.416 bar. 3.416 bar. Madhu Smita, you are saying, sir, for diatomic gas, gamma is equal to 1 plus 2 by F and F is equal to 5. Can we use this formula, sir? So what I will recommend, why to complicate things? Why to complicate things? We know these things. See, I'm trying to use the information, the formulas which you already knew, which you already have understanding about. We are here trying not to introduce some more new formulas. Okay, so that is why I will recommend you follow this rule. So there is no risk. You can do like this. Okay, so we have the value of critical pressure equal to 3.416 bar. We have the value of critical pressure is equal to 3.416 bar. Now tell me. We have given the value of back pressure. We have the value of back pressure is equal to 3.5. So what will be our P2, or we can say exit pressure? What will be our P2 or our exit pressure? We will use PB or will we use PC? Will we use PB or we will use PC? So we have seen what that when critical pressure is greater than back pressure, or sorry, when back pressure is greater than the critical pressure, we have no problem. So we can use 3.5 bar. We can reduce the pressure in this nozzle certainly to 3.5 bar. So we have the exit pressure. As 3.5 bar. If you have confusion, just see this. What we were doing here. I asked you all this question. You said yes or no. Okay. So I asked you if our critical pressure is 5 bar, can we reduce it to 10 bar? You said yes. Why you said yes? Because sir, that pressure is greater than the critical pressure. In same way here also, the back pressure is greater than the critical pressure. So we have to use the value of back pressure. We do not have to use the value of critical pressure. Okay. So which pressure we should use in this problem? Is that clear or not? Tell me, is this crystal clear to you or not? All the students in the live who are present in this live class can respond. Please respond to me. Is this clear or not? When to use back pressure, when to use critical pressure. Yash, sir, in Bansal and one foreign author book, formula of N is reverse of that you have mentioned. So you can check Bansal, the same formula is given to you. The same formula is given to you in Bunsen. The same formula is given to you in Bunsen. Do not worry. Do not worry about it. Okay? The same formula is given to you in Bunsen as well. Do not worry. Just open the Bunsen right now. And if you have doubt, I can open the Bunsen on this screen as well. You can check there. Okay. My dear friend, they might have used the reverse of I am using PC by P1. Just go and check that. Just go and check that. No worries. No worries. If they are using low pressure by high pressure, they might have been using the higher or lower value. This is a ratio. So in terms of ratio, I think in Bunsen book, it is defined in terms of N only. So see what is N. The formula is same. Do not worry. Just trust me. Do not worry. There is nothing to worry about. There is nothing to worry about. Okay, there is nothing to worry about. Right? Do not worry. Is that clear? Is that clear? Now we have to find stagnation upon inlet. You are saying Yash. Just believe me, the formula is same in Bunsen. Don't worry. Don't worry. Don't worry at all. Do not worry at all. There is nothing to worry about. Okay? Okay? So now, what we have to find this in question? What we have to find here in this question, we have to find mass flow rate per unit exit area. We have to find the mass flow rate per unit exit area. Yes, still having doubt? Still you are having doubt? This is the same formula that is given in the Bunsen. Do not worry. Do not worry about it. Okay. So we have to find the mass flow rate at the exit. So you know the formula of the mass flow rate is equal to rho 2 A2 V2. Rho 2 A2 V2. Yes or no? Rho 2 A2 V2. So we have to find mass flow rate m dot 2 upon A2, m dot 2 upon A2 is equal to m dot 2 upon A2 is equal to rho 2 V2. Rho 2 V2. Acha, just wait. Wait, I will open Bunsen here only. Don't worry. I will open here Bunsen here only. Don't worry. Just do not worry. I'll solve your confusion. Do not worry. Just see here. Just focus here. So we have to solve for m dot and A. We have to solve for mass flow rate per unit area. So m dot 2 upon A2 is equal to rho 2 V2. We can write like this. We can write like this. Yes or no? Write like this. Yes or no? So here we can choose to use that formula we have seen in the, see, we have seen this formula. We have seen this formula. This one. So we have the value of T1, we have the value of Cp, we have the value of N. We can use that formula directly, but I will say there is no need of memorizing that formula. There is no need of memorizing that formula. No need of memorizing the formula. So see here. So we have this nozzle. Let's apply the basic of thermodynamics. We have this nozzle here. This point is 1, this point is 2, and we know the value of P2. Now tell me, from steady flow energy equation, can I write like this? H1 plus V1 square by 2. H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. H2 plus V2 square by 2. Yes or no? H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. So from here, if I neglect the entry velocity, which is very less, we can write it like 2 times H1 minus H2. 2 times H1 minus H2 under root H1 minus H2 under root. This is what we got from steady flow energy equation. Now tell me, we know we know that H1 is equal to CPT1 and H2 is equal to CPT2. So if we are able to find the value of T2, will we be able to find the value of the V2? If we are able to find the value of V2, say yes or no. Say yes or no. See, no formula I am using. Not at all, nothing, no formula I am using. Just the basic of thermodynamics, what we already know, is steady flow energy equation we already know. So I am just using that. Or otherwise, we can directly use that formula that we have established for the exit velocity at the convergent nozzle. Exit velocity at the convergent nozzle. Okay, exit velocity at the convergent nozzle. So you have the value of P2 now. You have the value of P2. So we have P2 by P1. We have P2 by P1 to the power gamma minus 1 by gamma is equal to T2 by T1. This is relation what we are fond of using for isentropic flow. So we have the value of P2. P2 is 3.5. We are using the value of back pressure. We are knowing that we have to use the value of back pressure here to the power gamma minus 1 by gamma. So 1.667 minus 1 by 1.667. Okay, 1.667 is equal to T2 is equal to T2. Yes or no? Is equal to T2 by T1 is equal to T2 by T1. Yes or no? Is equal to T2 by T1. So what is our T1? What is our T1 here? T1 is 370. So can anyone tell me the value of T2 coming out of it? Can anyone tell me the value of T2 coming out of it? I have to calculate myself. Nobody is going to help me out. So this is coming out to be 280.38. Thanks for helping me, Aishwarya. Thanks for helping me, Frozen. Madhu Smita, I think you have made some typographical errors. So this is coming out to be 280 point what? 280.38. So we consider it 280.4. 280.4 Kelvin. So we have the value of T2. So from this equation where we have derived from steady flow energy equation, we can put the value of, we can have the value of V2 is equal to 2 times. So we have the value of Cp with us in the question 5.19. We have the value of this Cp in the question 5.19. We have the value of T1. Is equal to 370. And now we have the value of T2, 280.4. So can someone tell me the value of the exit velocity to the nozzle? Can someone tell me the exit velocity? Exit velocity. So what is the exit velocity? What is the exit velocity? What is the exit velocity? So it is coming out, as you are saying, it is coming out somewhat about 30.5 meter per second. 35.5 meter per second. Is it or isn't it? Is it or isn't it? Tell me. I think there is some mistake happening here, because velocity can't come this less, because in what we shall do, our velocity should increase. So before exit to the steam turbine, this much velocity is coming out. So something is wrong. Something is wrong. Okay, let me check. Give me a minute. Let me check the calculations. Let me check the calculations you have done. Let me check the calculation you have done. Just wait a minute. Just wait a minute. Oh my God, what a mistake. But so you guys now tell me, are you guys are doing something? You guys are doing something like, you are giving me the answer in meter per second. You are giving me the answer in meter per second by putting the value of Cp 5.19 kilojoule per kg Kelvin. Hmm? Tell me, you have to multiply 1000 here as well, na? 1000 is to be multiplied here, na? Yes or no? Yes or no? Because since the value of Cp is given to be, since the value of Cp is given to be, since the value of Cp is given in kilojoule per kg Kelvin, you have to multiply 1000 and then the velocity will come in meter per second. Then the velocity will come in meter per second and it will be equal to 964.4 meter per second. 964.4 meter per second. Got my point or not? Got my point or not? Yes or no? Yes or no? So this is coming out to be 964.4 meter per second. Okay. Now realize this thing. This mistake is also giving us something to learn. See how it came in my mind at an instant I seen this value. At the instant I saw the value, this came into my mind. This came into my mind because this came into my mind because as I am seeing the value so less, 30 point something. So before nozzle increases the velocity, so 30 meter per second is a very less velocity. So when you get the values like this, your value of velocity must approach to the velocity of sound. Velocity of sound. So this much velocity comes if in examination also this less velocity, this less value is coming, just cross check yourself. Just cross check yourself that what is happening, what is wrong happening with you, what is wrong happening in the solution. So we have the value of V2 is equal to 964.4. So we wanted to have, it was asked to us to find the value of mass flow rate with respect to area, mass flow rate with respect to area. So we have this mass flow rate with respect to area. So it is rho2 V2. So we have this value of V2. We have this value of V2. So how we will get the value of rho2? So P2 by rho2, P2 by rho2 is equal to RT2. We know that from ideal gas equation. Is that clear or not? Is that clear or not? P2 by rho2 is equal to RT2. So from here we can find the value of rho2. Here we can find the value of rho2, that is equal to P2 by RT2. P2 by RT2. So here you put the value of P2, you put the value of T2, you will find the value of rho2. You will find the value of rho2. So I am putting the value. So P2 is 7 bar. So 7 into 10 to the power 2. R I am putting in kilojoule per kg. So I have converted the pressure in kilopascal. I have converted the pressure in kilopascal, and we have to put our temperature as absolute temperature, that is 370. That is 370. Okay. We have to put exit pressure as 3.5. Exit pressure is 3.5. Our entry pressure was 7, so exit pressure was 3.5. Okay. So from here, and the temperature also was not 370. I am putting the condition of initial condition. So what was the temperature we calculated? We have calculated the temperature equal to 280.4. 280.4. So from here you can have the value of rho2, yes or no? From here you can have the value of rho2. What is the value of rho2? Can you tell me? What is the value of ρ2? Can you tell me? What is the value of ρ2? Can you tell me? What is the value of ρ2? Can you tell me? Anyone? What is the value of ρ2? Can you tell me? So it is coming out to be 0.6. As I am just writing the values you are telling me. Kg per meter cube, 0.6 kg per meter cube. You can put this in this formula. We have now the value of ρ2 and now we have the value of V2 as well. So you put this into this formula, you will have your m dot, you will have your m dot by A2. So your m dot by A2 will be 0.6 into 0.6 into what? 964. 0.6 into 964.4 meter per second. So what is the value of m dot by A2? What is the value of m dot by A2? So it is coming out to be, what is the value coming out to be? Can you tell me? Can you tell me? Mass flow rate per unit area. Please focus. Mass flow rate and per unit area was asked to us. So this is coming out to be 578.6 kg per second meter square. Kg per second meter square. So this is the answer to the first part of the question. So is this crystal clear or not? Is this crystal clear or not? From this, I wanted to teach you two things. Firstly, when to use the exit pressure as critical pressure and when to use exit pressure as the back pressure. So here we have used the exit pressure at back pressure because back pressure was greater than the critical pressure. Back pressure was greater than the critical pressure. Then I solved this question. By basic thermodynamic concept. The only new formula I have used here is this one. Only new formula I have used here is this one. So where is Yash? Yash, you had an issue with this formula. You had some issue with this formula. Are you there? Are you there? So now we can start solving the second part of this question. The second part of this question, find taking ethane in place of helium, whose Cp is equal to 1.88 kilojoule per kg Kelvin and molecular weight is 30. So yes, you still have the doubt in this question. You still have the doubt in the formula. Have you seen R.K. Bansal book just now? So still having doubts, so let me open. So by the time I solve the doubt of Yash, all of you please copy this question. Let me open the R.K. Bansal book and show all of you what formula is given there. Now please see this formula. Please solve the second part of this question. There is some technical issue happening. Please solve the second part of this question. So there was some technical error. So if you haven't copied the second part, please copy the second part. Please copy the second part. Please copy the second part. There was some technical issues, so that's why the video got stuck. Okay, but we are continuing now. Okay. So in second case, what is happening? In second case, what is happening? In the second part, you can solve the second part of this. Now, Yash, we have the R.K. Bansal book on the screen. And here is the formula. How is it different? You can see the formula. You can see the formula. How is it different? Tell me that. Tell me that. How is it different? Yes, we are having R.K. Bansal on the screen. We are having R.K. Bansal on the screen. And this is the same formula I am writing. Just I have written this ratio. Just I have written this ratio. Just I have written this ratio on the other side. I have written this ratio on the other side. Now see this formula and this formula. Both are same only. I can't find any difference in the formulas. Okay, let me now copy it. Yes. Please compare both the formulas. Please compare both the formulas. The one I have shown you on the pencil and one I have written over here. And that will be, I don't think, what's wrong with you. You are telling me, sir, there it is written gamma plus 1 upon 2. The same formula is on the screen, my dear. The same formula is there on Bansal. I have opened the Bansal live on this YouTube channel just to answer you, my dear. There also it is gamma plus 1 by 2. Here I have written the same thing. Is that clear now? On the live lecture, I think this is the first time some teacher has opened a book and showed this to you. That the same thing I am teaching. Isn't it? So coming back to the question, coming back to the question. Clear, Yash? So please see the things rightly or believe it. Or believe it. You were saying, sir, no, sir, no, sir, no, sir, no, sir. So you left me with no option but to open the book in YouTube live session. Okay? So please trust the teachers who are teaching you. Okay? Okay. Now, let's move further. So the second part of this question, the discussion was a little bit deviated. Now coming back to the point, coming back to the point, coming back to the point. Now the second part of this equation, the second part of this question, find taking ethane C2H6 in place of helium whose Cp is this and molecular weight is this. So if I start solving the second part, can you, what we shall use? Firstly, what shall be if we establish a procedure, if we just establish a procedure to solve the problem. So let us first try to find the value of PC. Let us first just try to find the value of PC here. So value of PC. So for that you have to find the value of PC. So for that you have to find the value of gamma. So in the question, what is the value of gamma given to us? So gamma is not given. In case of ethane, it is given 1.88 kilojoule per kg Kelvin. Okay. So we have our CP, is equal to 1.88 kilojoule per kg Kelvin. 1.88 kilojoule per kg Kelvin. Okay. 1.88 kilojoule per kg Kelvin. Yes or no? 1.88 kilojoule per kg Kelvin. So we have R is equal to Cp minus Cv, and we know R is equal to R bar by M. So R is equal to R bar by M means R bar is 8.314 divided by M, and M is given to be 30. M is given to be 30. Yes or not? M is given to be 30. So this is 8.314 by 30. So what is the value of R for ethane? Can somebody tell me? So then you are telling me 0.257. So this is 0.257. This is 0.257. So you can find the value of gamma, Cp by Cv, by again using this relation, R is equal to Cp minus Cv. So these two relations you can use, which you have been using in your classical thermodynamics as well. So can anyone tell me the value of gamma? Anyone tell me the value of gamma? Can anyone tell me the value of gamma, please? Can anyone tell me the value of gamma, please? Anyone? It is 1.172. It is 1.172. Is that true? It is 1.172. Is that true? Is that true? Okay. Okay. So now if I place the values in this PC formula, we have gamma is equal to 1.172 plus 1, and gamma 1.172 divided by 1.172 minus 1. So we can have the value of PC. R is 0.277, not 0.257. Okay. You guys are making calculations. I am not using any calculator. So whatever you are telling me, I am writing that. Okay. Okay. So now tell me, what is the value of PC? So those who are solving this problem with me must understand that this is giving you concept. So much concept this problem is giving to you. Now tell me what is PC. So PC is coming out to be 3.98 bar. 3.98 bar. Now listen to me very, very carefully, my students. Listen to me. In the first case, what was happening? In the first case, the PC was 3.416 and the PB was 3.5 bar. In this second case, our PC is 3.98 bar and our PE or PB, our PE or PB is given to be, our PE or PB is given to be, PB is given to be 3.5 bar. Now, is this possible? Is this possible? Can we do it in converging nozzle? Can we do it in converging nozzle? So no, we cannot do it in converging nozzle. We cannot do it in converging nozzle because here the back pressure is less than, the critical pressure. So this is not possible. This is not possible. Yes, Arpan. Yes, Arpan. This is a static pressure only, because stagnation pressure is a pressure where the velocity we assume to be 0. You can call the inlet pressure as a stagnation pressure, as we have assumed the inlet velocity as negligible. Okay. So PB is less than PC. Our back pressure is less than PC. So this is not possible in convergent nozzle. So what we have to use? We have to use P2 is equal to PC, that is 3.98 bar. 3.98 bar. Then with this P2, then yes, Madhusmita, the exit pressure will be equal to 3.98. Okay, we will reduce the nozzle to 3.98 bar, and the maximum velocity we can attain will be the velocity of sound. Okay, so from here you are using P2 is equal to PC, so you can find the velocity of V2. So somebody will put the formula what we have seen in previous once what we have seen lastly. V2 is equal to some big formula. Now see it. Someone can use again this formula V2. Okay. Someone can use again this formula V2. Someone can do what? Someone can use this philosophy of steady flow energy equation. What I will do, I know my back pressure is equal to critical pressure. So my exit velocity will be equal to the velocity of the sound. This is what we have seen now. When the exit pressure is equal to critical pressure, our velocity at the exit is nothing but the velocity of sound. Is that true or not? Tell me that. Okay. So we have the velocity. Just you need not to make any calculation. If your exit pressure is equal to, you are putting it equal to the critical pressure. So definitely at that critical condition, your velocity is coming out to be equal to velocity of sound. Your velocity will be coming out to be equal to the velocity of sound. Is that clear? So when you have V2, you can find ρ2 as well. You have the temperature T2. So ρ2 will be P2 upon RT2. Okay. So as you are operating on critical condition, you can say like this also, that this exit density is equal to the critical density. And and you can place the value of critical pressure, critical temperature here, and you can have your density, and from then you can have your mass flow rate, you can have your mass flow rate rho 2 V2, or in this case it is equal to rho C Vc. So from this question, is it clear? Everyone who is live must respond to me. All the concepts of design of nozzle before it enters to the moving blade, before our steam enters to the moving blade, is that clear or not? Is that clear or not? In the first lecture, I told you that we are going to unfold the steam turbine layer by layer. We are going to unfold the steam turbine layer by layer. So I told you in the first lecture that a steam turbine is a combination of nozzle and moving blade. So at this point, can we say we have unfolded the nozzle in all the possible respects? In all the possible respects? Yes or no? Yes or no? Tell me. Yes or no? Is that clear? Is that crystal clear or not? Is that crystal clear or not? So if any questions would be asked to you in nozzle, you will be able to answer if you have understood these concepts and all, if you have understood these concepts and all. So what you can do now, you can go and solve some more examples out of any textbook. You can choose RK Bansal, you can choose power plant by PK Nag, you can choose. Okay. So from these you can solve it. From these, you can take up some numericals and can solve it. And we at the GATE Academy also will try to provide you some questions of this new additional GATE syllabus topics. From there, you can understand the concept. From there, you can practice and solve the GATE questions. So our first section of analysis of a steam turbine is hereby almost completed. A few things are left that I will discuss very, very quickly, but almost our first section of a steam turbine is completed, where we have analyzed the very essential part of our steam turbine, that is nozzle. So here in this lecture, what we have got the understanding of a steam turbine as well as the compressible flow. So two of our topics are simultaneously covered in this session. So if you have liked this, please tell me in comment what is your feedback, and also subscribe the GATE Academy. Also subscribe the GATE Academy. You can give your feedbacks in the comment section. Those who have done all the lectures, till now must have a lot of clarity in the nozzle as well as compressible flow. Is that true or not? Correct or not? You can give me your feedbacks in the live session, and I request you to subscribe the GATE Academy channel. Okay. So now if I tell you the steps of solving a nozzle problem, first you find PC. This critical pressure you find first. Thank you all. This critical pressure you find first, then see the condition. If back pressure is given to be less than the critical pressure, use exit pressure or the final pressure at the exit of nozzle at PC. And if PB is greater than PC, if PB is greater than PC, we can have P2 is equal to PB. 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 Okay. And then following the steps by using general thermodynamics, I have tried solving the question by using the general sort of general thermodynamics concepts and general fluid mechanics concepts. So for that, first we need to find the critical pressure. So for critical pressure, we need to have the value of gamma. So let's just note down the value of gamma for various things. So gamma of air is we know as 1.4. Gamma of 1.3 we will use for superheated steam if nothing is given. If nothing is given, you can choose these values. You can choose these values. If gamma is equal to 1.135, it is for saturated steam. It is for saturated steam. It is for saturated steam. If gamma is equal to 1.035 plus 0.1x, you can use this for wet steam, where x is the dryness fraction. So these are the values of gamma that you can use for general steams, and then solve for the problems of the nozzle. The problems of the nozzle. So the nozzle problems you can easily solve. Nozzle problems you can easily solve by using the values of gamma. So you first have to identify the value of PC. Then you can do like this. So here we have seen, if you follow some books, you will see some of the diagrams like this. Some of the diagrams you will see like this. Let us explain a little. Let me explain a little of these diagrams. So whatever I have explained to you, you can understand from here as well. Okay, from here as well. So as I said, the entry to the nozzle. Is represented by O. The exit to the nozzle is represented by E. And this back pressure, what is this PB? This back pressure is controlled by this wall. Okay, so we are controlling the back pressure. With the help of this wall. Okay, so with respect to the back pressure and our critical pressure, our exit pressure may vary. So you can see here 3-4 lines. So in the first line, what is there? If P naught is equal to PB, means the entry pressure and the exit pressure are same. So there will be no flow, as I told you, or as you already have this understanding that if there is no pressure difference, there will be no flow. As there is no pressure difference, there will be no flow. So when there is no pressure difference, there will not be any flow. Okay, so this is what this first line is representing. This second line is representing what? That pressure 2. In the second line, the pressure 2 is greater than PC, as we have mentioned. Okay, 3 also, the pressure 3 is also greater than PC. And this pressure 4, as you can see, this pressure 4 is equal to PC. So as we have developed our understanding, we cannot reduce the pressure below the critical pressure. In convergent nozzle. We cannot reduce the pressure below the critical pressure in convergent nozzle. This is being shown by this diagram 4. So if the pressure is to be further reduced, you have to reduce it in this region. You cannot reduce it in the nozzle. So then you have to take the help of the valve and you have to change the back pressure, that is PB. So these waves are showing the changes in PB, but the pressure do not change inside the convergent part of the nozzle. Is that Is that clear? So, Arpan sir, in the industry, pressure valves installed on pipe measure the static pressure of fluid inside the pipe or what? It depends. You cannot say like that. It depends. It depends at what point pressure you are measuring. Okay, you can't generalize this thing. Okay, if the static, if you are measuring the pressure of a static fluid, you will get the stagnation pressure, like velocity is zero, so you will get the stagnation pressure. At any other place where the fluid is flowing, you will get the static pressure. Okay, Arpan? So is this clear or not? Is this figure how they have built it? Why I am showing you this figure? Because this type of figures can confuse you in future. That's what is happening in this, oh, this and that, this and that. So don't get confused in it. Don't get confused in it. Okay? Don't get confused in it. Okay? So let us conclude now. Let us conclude now our nozzle part with one last thing, that is nozzle efficiency. With the nozzle efficiency, and then we will be entering into the impulse, and we already are learning the impulse turbine only. If somebody is thinking, sir, we have come to learn the impulse turbine and we are learning the nozzle, so let me tell you the nozzle is nothing but the part of impulse turbine. No. So this is also the lecture, we named it as Impulse Turbine Part 1, because nozzle is an integral part of impulse turbine, or we can say without the nozzle, impulse turbine, there is no meaning of impulse turbine. Okay, so impulse turbine part 1 portion also we have explained how the nozzle should be designed in the impulse turbine. How the nozzle should be designed in the impulse turbine. So let me move a little forward with the nozzle efficiency. Okay, nozzle efficiency. So why we are using this term nozzle efficiency? Because in actual, we have considered the flow inside the nozzle as isentropic. We have considered the flow inside the nozzle as isentropic, but in actual, there is friction. In actual, there is friction inside the nozzle. So in nozzle, we have assumed the flow is isentropic, but in practical, in actual, the flow is not isentropic, but adiabatic. So we have to compensate this by a term that is known as nozzle efficiency. We have to compensate it with a term that is known as nozzle efficiency. So nozzle efficiency is nothing but why we are incorporating this word nozzle efficiency, because in actual, due to friction, the flow of gas or steam or superheated steam is in the nozzle is not exactly isentropic. So to compensate for that difference, we incorporate a term that is nozzle efficiency. So nozzle efficiency is nothing but actual enthalpy drop, actual enthalpy drop upon the theoretical enthalpy drop, which we have assumed to be isentropic enthalpy drop, because we have made this assumption that in the nozzle, the flow of the steam in the nozzle, the flow of the steam is in the nozzle, the flow of the steam is isentropic, okay, which is not actually isentropic. So we are incorporating a coefficient, to compensate for that difference between actual and theoretical thing. Okay, so what we have assumed, let's say what we have assumed. So let us see this by the help of a diagram. So if I make the enthalpy entropy diagram, you can make any diagram, you can make TS diagram also, you can see from that also. So enthalpy entropy diagram saturation curve is somewhat like this, some temperature curve is somewhat like this, and we have these lines, we have these pressure lines like this. So here is the point of entry to the nozzle. Here is the point of entry to the nozzle, and we have assumed, you can see it from TS diagram as well, no problem with that. So we have assumed that the flow of steam inside the nozzle is isentropic. So this H naught minus H2 represents what? This H naught minus H2 represent isentropic enthalpy change, or isentropic enthalpy drop, or isentropic enthalpy change, whatever you will want to say, you can say it. So this is our isentropic enthalpy drop. This is our isentropic enthalpy drop. Now, what is the actual change in entropy? What is the actual change in entropy? What is the actual change in entropy? As the flow was not isentropic in practical, so our entropy will increase. Our entropy will increase, and let us say this point is 2s. Let us say this point is 2s. So H naught minus H2s, H naught minus H2s will be H naught minus H2s will be our H naught minus H2s will be our actual enthalpy drop. Actual enthalpy drop. Okay, so the ratio of these two we define as nozzle efficiency. The ratio of these two we define as nozzle efficiency. So again, doing the same thing, if between 0 and 2 I apply the steady flow energy equation, we can write like this: H naught plus V naught square, same thing I am doing. I am applying the steady flow energy equation as we are applying in our general thermodynamics or classical thermodynamics. So at point 2, it will be H2 plus V2 square by 2. This is our steady flow energy equation. So we can write H naught minus H2 is equal to V2 square by 2 minus V naught square by 2. Yes or no? So what is our nozzle efficiency? So nozzle efficiency is actual entropy drop. Actual entropy drop is what? H naught minus H2s. And what is our theoretical entropy drop? It is H naught minus H2. That is isentropic. Sorry, actual we are representing by 2. And isentropic we are representing by 2s. So H naught minus H2 upon H naught minus H2s. This is our nozzle efficiency. So if I place this, so I can write like V2 square by 2 minus V naught square by 2. I'm just replacing what in terms of velocity. I'm replacing the things in terms of velocity, nothing else. Okay, so we have V2 as a square upon, this is V naught. Okay, this is V naught square by 2. So from here, we can write our nozzle efficiency is equal to, if I neglect this V naught, I'm neglecting that. Because as you have seen, till now we are making this assumption that V2 is very much greater than V naught. So I am neglecting it. So what will it become? It will become V2 square upon V2 as a square. V2 as a square means we have a new formula. We have a new formula of nozzle efficiency. Is that right or not? We have a new formula. So if we have the velocity, actual velocity, V2 represent what? Actual velocity at exit, actual velocity at exit. Okay, okay, and V2s is what? V2s is what? V2s is isentropic velocity at exit. So we have done whatever till now, we have assumed it that whatever we have done till now, we have assumed till we have isentropic velocity at exit. So whatever we have done till now, whatever we have done till now, whatever we have done till now, we were finding the isentropic velocities and everything in isentropic conditions. So if in actual isentropic condition do not happen, or if any question isentropic condition do not happen, you will be given a term as nozzle efficiency, or sometimes in general we call it isentropic efficiency. So you can relate it in terms of velocity, you can relate it in terms of enthalpy drop, in terms of enthalpy drop. Is that true or not? Or here we can define a coefficient as well. Phi is equal to V2 upon V2s. So I have represented 2s here. Okay, sorry. So just shift it, no problem. We are calling 2s as isentropic, and just a minute, because 2s is generally represent isentropic drop, because we have put isentropic there. So let me make it actual and let me make it isentropic. No problem. Let me make it isentropic. Is that clear now? Okay. Because two S terms we generally use now for isentropic. Previously also it was not wrong, but just that you have to use that value accordingly. So in sake of remembering formula or identifying the formula, we are making this correction. Otherwise, there was nothing wrong in that also. Okay. So we have phi is equal to V2 upon V2s, and we call phi as velocity coefficient. We call phi as velocity coefficient. Okay. So what we can do, one other formula we have arrived with, that nozzle efficiency is a square of velocity coefficient, is a square of velocity coefficient. Okay. So today's session is clear or not? Is this session cleared or not? Okay. We are entering into the moving blade now. We are entering into the moving blade now. Now, in the first lecture, what we have seen, where we were at the point where we have seen the exit steam from the boiler enters the steam turbine. Then we broadly unfolded it in the nozzle and the moving blade. Now, by this point, we have understood in all respect that what happens inside the nozzle, how the velocity get increases, how to make the nozzle, what shape it has to be, what kind of cross section, converging, diverging, or both converging and diverging, where should be the throat, by what velocity we can increase, in the nozzle. Okay, critical condition, everything with respect to the nozzle we have seen. So impulse turbine, half part of the impulse turbine is completed by this video. Why I'm saying so? Because impulse turbine, as I told you, is a combination of nozzle and moving blade. So nozzle part is completed. In all respects. So we can say half of the impulse turbine thing is completed here. So in the next session tomorrow, we are going to see what kind of impulse turbine, what kind of moving blades we are having, and how to arrange these moving blades, what are the stages and what are the everything, how to make the velocity diagram, how to approach with the velocity diagram. We are going to see all that in tomorrow's lecture. Okay. So is it fine till now? You can reply back in the chat to me. You can reply me back in the chat. Thank you. So please subscribe the GATE Academy channel as well as Hindi channel. Okay. And please ask your friends also to come see and attend these live lectures. This is only for the benefit of you students. Okay. Only for the benefits of you students we are doing this. Okay. So please have the maximum benefit from it. Okay. Certainly you have to solve some more numericals, but certainly you have to solve some more numericals, but this much discussion is more than sufficient according to me for your gate 2020 preparation. So if you have liked it, here we are seeing all the technical contents. We are not talking very much. We are just focusing about learning. Okay, so please ask every friend of yours to come and subscribe, subscribe, share this the Gate Academy channel. Okay, so that you will have more such good videos, good content, and you can see it. You will get the notification of it. So now please ask any doubt. If you have one, you can at this point of time can ask the doubt. Otherwise we will meet each other in the next session. I'm asking any live students is having any doubt. Now can please ask me. Now can please you can ask me. Is there any doubt? Is there a doubt? So thank you very, very much. I hope you enjoyed this video. If you are seeing this video directly, please watch the previous videos as well. And this is not the last video of this series. Okay. Tomorrow we'll be live. We'll be uploading new videos. Will be live at 10 a.m. in the morning. There we are going to see the types of impulse turbine. There we are going to see the types of impulse turbines, how we stage them, how to find the maximum blade efficiency and everything. Okay. So I will meet you tomorrow. Okay. Thanks for watching the video. Thank you very much.